It's a great pleasure to be here and talk about the topic that I'm passionate about. Coordinate systems for complex, large-scale sensory systems. If I get started, so I'm with Clearwater State University. We have about 10 graduate students currently, have several ongoing projects, and the particular talk that I'm going to give is related to this project that we started as virtual sensor networks that evolved into many areas. So I will talk about that. And interestingly, this work recently has been extended to other areas such as social networks. So I will briefly touch on that topic. All right, so we are talking about coordinate systems for large-scale sensor networks, complex large-scale sensor networks. So when we talk about complexity, maybe we can take a short-term view, like next 1 to 4 years, and we can take a long-term view, maybe beyond 5 years, right? So I think some of what I'm saying are applicable to short-term networks, and later developments that I talk about will be applicable for these other types of networks. So that as far as the scale is concerned, there's this buzz about Internet of Things, so many 50 billion devices by 2020. Now, just because we have these sensors and IoT devices that are connected to Internet does not mean that the network itself is going to be complicated, right? So you may have some devices connected to the walls, but they are talking to a Wi-Fi hub or something that's not going to increase the complexity. But within this, there will be islands of sensors, sensor networks, where we have to address the individual nodes. So that is kind of the subset that I'm talking about. Right? So over the long term, we are talking about these technologies that will form very complex networks with large number of sensors that have limited capabilities, like traditional wireless sensors, maybe not energy limited anymore because of power harvesting, but there will be large islands of sensor networks that are monitoring things. So that is kind of where we started, and then let's take an example like this here, a petroleum refinery, right? So the vision is that you will have maybe tens of thousands, if not hundreds of thousands of sensors in an environment like this here. Can we deploy sensor networks in an environment like this? It's very unlikely. If you have sensors that can detect corrosion in pipes and you want hundreds of thousands of sensors in this area, it's a very harsh environment. Signals get reflected, attenuated. You can have two nodes that are next to each other within 1 foot of each other, but there's something in between, so this can't communicate. So this is the complexity that I'm talking about, right? So the large scale is one thing, the complexity is something else. Right? So complex topologies, layouts with obstacles, harsh environments with interference, and multiple paths. So in these circumstances, we want to be able to address these nodes. So how do you address these nodes? This is what the talk is about, coordinate systems, right? So I will, in the talk, my outline basically is physical coordinates, virtual coordinates, and topology coordinates. But in the process, I will be, you cannot evaluate, you cannot think about a coordinate system, you cannot just give some coordinates and say, oh, I'm done. It has to be useful for things like localization. How do you obtain these coordinates? Routing, mapping, tracking, and we have this new idea called network awareness. Right? So that's what I'm going to talk about. And then very recently, coincidentally, we've been working on other projects related to social networks and other things, and we realized that what we have really done is actually develop a coordinate system for graphs, where nodes and edges are there, and you can kind of think about these graphs as in terms of coordinates. So ultimately, this is a long-term view. What I would like to do is really develop an analytical geometry for graphs, where there's nothing like that, right? But that's the far vision, and we are nowhere close to that. So this is what I want to talk about. So let's start with sensor networks, and we'll gradually start talking about. So in sensor networks, how do you do addressing? So in the early days of sensor networks, and still there are networks, where the argument was, well, these networks are going to be complicated, and the nodes are going to be fairly primitive, and therefore we don't want to even allocate an address to these things. Right? So there are these schemes like rumor routing and gossip routing and other schemes that were developed. So in this case, for example, the nodes don't have any addresses. The address really is content. So this red node has something to tell to the others. right? So it sends a rumor or it sends these random messages around that gets propagated, passed around among random nodes. So this is what we call a rumor. And somebody else is looking for that information, right? Sends a query, I'm looking for this type of information, and if this query happens to run into one of these nodes that know about this contents, it can follow it from there and get to the source of information and obtain the information following the same path. So this is what we call rumor routing. You don't need an address. But I start with this one because we will actually make use of this later on. On the other hand, much of the effort has been in providing network addresses based on some kind of coordinate system. And a lot of effort has gone into using physical position as the coordinates of a node, right? So how do you identify? You deploy sensors and now the nodes have to self-localize. They will find their position, X, Y, Z, longitude, latitude, elevation, whatever, using techniques like GPS or time delay or RSSI, receive signal strength indicator. Right. GPS is not available everywhere, especially in these harsh environments that we are talking about. If you use GPS, it's going to significantly increase the cost. Time delay, well, to get time delay, in this case, you have to synchronize the clocks. Right? Synchronizing clocks is a more difficult problem than getting the time delay. So you can use it, but again, scope is limited. Receive signal strength indicator, a lot of work, if you look at hundreds of papers, where you use some kind of a model distance, this is how the signal strength varies. We use this mean model and estimate the distance. And if you know the distance to 2 nodes or 3 nodes, you can localize yourself. But even under the best of circumstances, there is fading and your receive signal strength is way off. When you have interference and reflections and other things, it's impossible to use. Right? I'm not saying it's a bad idea, it's worth doing research into, but I've seen places where they have used this technique and you walk into a lab and the modes are hung right between the ceiling and the floor and it works in that environment. But the moment you go to that refinery or someplace, this will not work. Right? Now suppose you can obtain the physical coordinate somehow. My argument is, well, first of all, it's unreliable, infeasible, and costly in many of these conditions. And even if it is available, it may not be that useful. Right? So I take 2 examples. Right? So here there's a network in this area, and there's a void here. You know the physical location, right? Long time back, we did not give our coordinates. Now we can give GPS coordinates of your home so that your friend can visit you. But in the absence of that, so if you have only the coordinates, you send a message and you come to a void and now you don't know which way to go, right? So for example, with 2D, there's this well-known algorithm, GPS app, where it basically goes to some place like this, make a right turn and keep going until you can overcome this obstacle. Now this is in 2D, right? In 3D, when you go to a concave void, there's nowhere to go, there's no right, left, and it's 3-dimensional, right? So the probability of going in the right direction, in this case, is almost 0. So for 2D, it has a chance of working, but you go to 3D. So my argument is physical coordinates are not useful without roadmaps. We can give coordinates now because there are maps. Maps are available, therefore you don't have to give the street directions, go this way, turn here. You don't have to give that, you can give the coordinates because the map is there and you can route. So in the absence of maps, physical coordinates are useless. So, as I said, so what is the alternative? We have to go to some kind of a virtual coordinate. Right? So this is what I'm going to introduce next. Again, this is a fairly, people have worked on this idea of virtual coordinates. Now if you are checking email, just pay attention to this slide because if you don't follow this slide, rest of the talk is So you have a network, right? Some nodes randomly decide, hey, I'm going to be an anchor. So these red nodes have decided to become anchors, right? So in this case, we don't measure in distance. The red node says, hey, I'm an anchor, I'm at a distance 0 from myself, tells its neighbors, they know they're at a distance 1. There's their neighbors, they know they're at a distance 2, distance 3, distance 4, right? So this is an ordinate in this virtual coordinate system. It's a distance in hops to a to an anchor node. So we don't measure signal strength, we don't measure time delay, it's whether you can communicate with somebody or not, right? So in this case we have, and also you can see that these coordinates actually propagate radially away from the anchor. So one of the things that happen is you have lost the concept of right, left, that's gone, right? And then there's a second anchor, so the coordinates propagate radially, and then there's a second anchor, so in this case the coordinates would be like this here. Right? If you don't have enough anchors, there will be identical coordinates, and you don't know how to place anchors, and so there are a lot of problems. So these virtual coordinates actually depend on connectivity of a graph. So this is more natural for graphs and networks compared to the physical coordinates. Right? So I take this rectangular grid so that it's easy for you to follow. So I have these coordinates. There are 4 anchor nodes, so each node has this tuple that describes how many hops to reach A, that's the first coordinate, how many hops to reach B, that's the second coordinate, and so forth. Now in this network, if there happens to be an obstacle, what happens is the coordinates are different, right? So the coordinates take into account the connectivity, but they have lost all the information about the direction and everything. So again, this is fairly old work before us. So the virtual coordinates depend on connectivity and are easy to generate and can be reliably generated. So there's this scheme called logical coordinate routing, for example. What you do is, well, you know the coordinates. So this is the coordinates of P, coordinates of S, S's neighbors. So what you do is you want to send a message from S to P, you calculate the distance from here to here, your neighbors to P. Well, in this case, S to P is 16.85, N1 to P is 16.25, N2 to P is 18.14. Well, this looks closer, so you give the message to you give the message to N1, right? And you forward this gradient. And you calculate the distance using this here, the Euclidean distance. But if you look at this, these are not orthogonal axes, these are just hop distances. So if I happen to have 2 anchors close to each other, those are highly correlated, they are not orthogonal to each other, right? But this is kind of where we started. All right, so, and then there are other problems. How to find the optimal number of anchors? Because if you want to find the optimal placement of anchors, you want to know the number of anchors, but the number of anchors depends on the placement of anchors. So this is a very, very difficult problem, right? So effectiveness depends on anchors, but the selection of optimal set of anchors is difficult. So very often, at least in the earlier work, people selected these anchors randomly, and that's where we will start. So here, kind of think about a 15 by 15 grid of rectangular grid of nodes. So in this case, there's this set of nodes on this one. What we have plotted is actually the distance to this particular node based on this coordinate system, and we have used 3 anchors. So this node is at a distance 0 from itself. But you can see if you want to come to this place now, you have to sometimes climb up. You have to go higher distances. In other words, just because we went to this connectivity-based thing, it did not avoid this void. So instead of the physical voids, now we have to climb these hills. It introduced what we call logical voids. Right? So this surface go from one place to the other. Actually, it's uneven. So it introduces problems, and this is kind of where we got started at the very beginning. We decided to select 3 anchors at a time and overcome this and come up with somewhat better performance. So just to give you some idea, so this red line is GPSR. This assumes that the physical coordinates are known. Right? This is the logical coordinate based routing, and we came up with a scheme that kind of approached GPSR. But we were really tinkering around the edges. We were not really doing anything fundamentally different. So this is when actually, so to sum up, virtual coordinates, you don't need any geographical localization or anything, but the problem is you have logical voids and then you have lost this directionality completely. So this is the point at which we kind of came up with this idea called topology coordinates, and what it is like this. So this is a network, and each of these rows is a node, right? And these are anchors. So this node is at a distance 9 from anchor A, 3 from anchor B, 8 from anchor B. So this is what describes this network. And if you give this to somebody, actually it's almost impossible to draw this network. So the conventional wisdom was basically this anchor-based thesis, lose the directional information. There's no concept of left, right, up, down. Physical information, whether that the fact that there are holes in this one and this is a circle, all this is lost. It's just a graph with the number of forms, right? This is kind of where we started. And then back in 2010 LCN, we presented this paper where we were able to go from here to obtain maps of these networks that have these features. You can kind of see the resemblance, right? And this is actually that's the starting point. So at this point, don't worry about the mathematics. There's a method. I will show you what we do. So we start with this set of coordinates. There's a matrix. We do a singular value decomposition. For those of you who are familiar with singular value decomposition, it's been around for more than 100 years, standard operation. So you take this matrix of coordinates, you decompose it, and then you come up with a new set of axes, right? So PCA essentially is, you start with some coordinate system. The axis may not even be orthogonal, and so forth. You start with this one, and what this transformation, well-known transformation, does is it gives you a new set of axes. These axes happen to be orthogonal to each other, and the first axis happens to contain most of the information, the next one, the next most, the next one, the next most, and so forth. So we started with these things that were not orthogonal. These are the virtual coordinates. We convert it to this one, right? But these happen to be orthogonal to each other. And normally when people use principal components, they keep the first one that has the most information, and so forth, and they start dropping things from the lower side, the far side, right? Now instead what we did was we actually dropped the first one, and we plotted the second one against the third one. So this was what we presented in LCN. And when we did that, we found that, well, we can recover this, right? So this actually came across in an accidental way, but we did this. So why do we throw away the first one? Because remember, this virtual coordinate propagates radially. So the first component actually contains this radial information. You throw that away, suddenly you get this geographical relationship, right? So at the time, in a couple of papers, we, taking the PCA of large matrix is not a sensor network friendly way. So we came up with another method to estimate that, using the number of, using a very small matrix and so forth. So I'm not going to go into that. But you can do it in a distributed environment using sensor networks, right? So in this case, this is the original network. These are the anchors. These are the maps that we obtained. Our reviewers always wanted to compare with this MDS, multidimensional scaling, which is actually not applicable in this case, because if you have all the information to generate that, you don't need anything else, right? So these are examples of maps that we use. So you can see the maps are distorted. Right. So my argument, actually at the time and even now, is that's okay. Why do we need physical maps that are to scale? Because we are used to it. We are used to the geometry. But if you look at certain examples, like if you look at the map of a subway system, a metro system, it's never drawn to physical scale. In fact, this distortion is much better than the original map, right? If you look at the bird's eye view of a certain area, this is not to scale. In fact, our vision is not to scale either, but we can navigate and do all the things. So why do we insist on having the actual physical scale? In fact, that is not natural for networks, right? For us, we have, we can see, and we have multiple sensors, but networks, you can only see your neighbors. So this is not natural, right? So that is my argument. In fact, if you use networks like this, and you use greedy forwarding to get from a source to a destination, in case of physical coordinates, actually this is 4A. In this case, only 40% of the time do you get correct forwarding. But in these distorted maps, you get much higher correct forwarding, because the distortion in this case actually corresponds to the connectivity, right? So this is a more natural coordinate system. More random networks, original network, the map that we created. If you consider a network like this here, these two can't talk to each other. If you draw this map we call topology preserving map or topology map, is something like this here, right? But if I add a node here so that A can go to B, talk to B via that node, what would happen to this one? This becomes a circle. right? The map is distorted, but the distortion is based on connectivity. And we can obtain this very, very, very easily. If you increase the communication range, you get maps. The nice thing is this naturally extends to 3D. In case of 3D, we drop the first component, take second, third, and fourth, and plot them, we get these maps. Right? So these we call topology preserving maps. So this is what we presented back in 2010, and we had a more extensive journal paper in transactions. And 20 papers later, so many graduate student theses, a couple of students at UNSW, a couple of students at UCF, part of their work is related to this. And in the process, I have started collaborating with many of you know Damla Terwood from UCF. She's applied this to the case where there are mobile nodes. Andrew Serkin, he's a control theorist, he's a theoretician working in control systems. And Randy Paffin wrote that Worcester Polytechnic, he's actually a data scientist. Right? So we have done a lot of things, and what I'm going to try to do in the next half hour is kind of to give you some idea of the things that we have done. In fact, this particular paper, I wouldn't call it planting a seed, but it was really like a spark, you know, that ignited the whole thing. And we have so many ideas to pursue in this domain. Right? So the way I think about it is, you know, think about some faraway civilization where there are really intelligent beings, but they can't see. The only thing they can do is touch their neighbors. And they come up with a geometry for that planet. Right? They wouldn't have developed our coordinate geometry in 3 dimensions. They would have developed a geometry based on these hops. That is what we need to use in sensor networking and other networks. Right? All right. So at this time, you know, we went from this case of where people thought that the logical coordinate do not have any information about the physical layout and other things. We were able to show that you can actually obtain that. So now we were sure that this information is there. So we were trying to figure out, can we get this information without doing a principal component analysis? In fact, there should be multiple ways to get that, right? So I'll give you a simple example here. So in this case, there's a straight line. This is an anchor. So this is 0 with respect to itself. This side a distance 1, distance 2. So this is how the first virtual coordinate changes. The second anchor is here. So it is at a distance 2, about 0 from itself, 1 this side a distance 1. So this is how the second component changes. Right. So if I take the sum of these two and the difference of these two and multiply them with each other, or take the square of one and subtract the square of the other, I get this line. So I have gone from this virtual coordinate that lost the direction. I combine two of them, and suddenly I have the direction. Right? So it's an illustration in 1D. So we can apply it to like a 2D network. I select this point here and this point, two random anchors, and the color actually corresponds to the virtual coordinate 1 squared multiplied by virtual coordinate 2 squared. So what I have done is basically in this graph I have imposed this like almost like latitude lines corresponding to this direction A1, A2. Right? So in the graph now I can identify two nodes, and I can say this direction is AB, and somewhere else in the graph I can say, oh, going from in that direction, go 5 hops and you will go from here to there. Right? So now we started with this connectivity and we developed this concept of directions in the graph. Right? So at this point, it results in, so this is what we call directional virtual coordinate. So our original intention is, well, PCA is too complex. Let's try to figure out another way to get topology coordinates. Well, we found the answer through directional virtual coordinates. And later it turns out that this has its advantages on its own, and even if it has nothing to do with topology coordinates, you can actually do marvelous things with directional virtual coordinates. So let me try to illustrate some things. So again, you know, some papers appear in this area. So let's see the interest of time. So here, again, I'm using a rectangular grid. So each of these numbers is actually a node, right? So I start with the virtual coordinates. I select these two anchors and calculate the virtual coordinate with respect to this one squared minus this one squared, and these are the resulting numbers. Right? So this is the directional virtual coordinate of a node with respect to direction A1, A2. If I take this one and this one, I get a different direction, and these are the coordinates. So if you are describing the same data set using two sets of axes, in other words, you have the coordinates for all these points using this axis, and you have the coordinates for all this using this axis, you can actually try to find the angle between these, right? So in this case, we use our, instead of the actual physical coordinates, we use our directional coordinates. So I take a pair of nodes at a time, and I find every point with respect to this direction, this direction, this direction, and from that I try to find this angle. And for this rectangle, a full rectangle at least, you look at it and they resemble the physical angles, right? So this tells us, well, maybe you can have a concept of angles in graphs using directional coordinates, because directional coordinates, it says in this graph, the direction AB that's specified by these two actually pervades throughout the graph. And now I have these directions and I can have this concept of angles, right? So in this case, for example, this is our network that I used earlier. I use these anchors, and if I look at, for example, the angle between AB and EB, AB is this two pair, so there's a direction that goes this way, and EB, which is the direction that goes like that, the angle between them is 56 degrees. The angle between DB and EC is 85 degrees, right? So now if I select DB and AC, those are like almost at 90 degrees. So I plot the coordinates of each of these nodes in terms of the directional virtual coordinate for DB and directional coordinate for AC. I should get some good plot, right? So this is the plot I get. So just by taking one squared minus the other squared and finding this, now I can plot this without going to the singularity decomposition. So that's another map. The distortion is different. This is a circle with 3 holes, 4 anchors, and so forth. So in the process, actually, we also came up with a heuristic for identifying anchors. Remember, I said identifying these anchors is a difficult problem. Actually, I think it's like an incomplete problem, but we have a fairly good heuristic. So multiple networks, from that point on, we call them extreme node search anchor selection. So we applied it to like 3D. This was LCN 2014, and we create these graphs. You can do boundary detection purely using these coordinates. You don't need physical coordinates. You can monitor boundaries of phenomena being monitored, and so forth. So this is not published work, but in this case, for example, we have this network, and I'm generating directional virtual coordinates with respect to A and B. It's nothing but the virtual coordinate B squared minus virtual coordinate A squared. Right? And then, so these blue and red nodes that are here, the only thing they know is the distance from number of hops from B and number of hops from A, and from that they calculate the directional virtual coordinate, and now they talk to their neighbors and ask, hey, what are your directional virtual coordinates? And from those alone they can say which latitude line and which longitude line they are on. Right? Part of the nodes fail. These guys don't know where they are based on that information, but these guys can say that. So now you can actually say, to route a message from this node to this node, I can say go in the direction perpendicular to AB, go along the direction AB for this many hops, and turn and go in the direction AB for this many hops, perpendicular to AB for this many hops. In other words, in a graph, now I can give directions. Go in this direction for 5 hops, turn in this other direction for 7 hops, and turn in this other direction for 3 hops, and you are home. Right? So this is again a new concept. All right. So we started with the virtual coordinates. We came up with these topology coordinates. Just because we came up with topology coordinates, we started with these, right? So we don't lose this information. So at this point, it was obvious, well, topology coordinates are somewhat like geographic coordinates. You have a distorted map, so you can still get onto concave voids. Logical coordinates, they have their own logical voids. So if you want to do routing, if you get stuck here, just go here and do routing. If you get stuck here, just go here and do routing, because we have both the coordinate systems simultaneously, right? So we came up with this idea called geological routing that was in this paper. And so in this case, the idea is you start in one coordinate system. If you get stuck in that coordinate system, you go to the other coordinate system, go around, and actually we had a third mode, and then you get to the destination, right? So in this case, we look at the performance. Again, I am using these 4 networks, And GLR, we had two cases. One is using random anchors, the other one using our ELS anchors. So this is red and blue lines, and this is the routability. And this is the spiral network, the circular network with 3 holes, the building network, and this other network. So all of this, you can see that this scheme actually outperforms TPSR. This is the scheme that needs the physical coordinates. Right? So without using the physical coordinates, actually this outperforms the scheme with physical coordinates, except in this one. This actually corresponds to the building network. It's a fairly regular, rectangular kind of a network, and they are actually work. But it does require physical localization. And then the problem with all these things is that if you look at routing algorithms for sensor networks, right, there are a lot of routing algorithms. All of them are designed assuming a 2D structure. Sensors are deployed in a plane, and I can localize and I can do this routing. There are few algorithms for 3D structures, but they don't work well for 2D. 2D algorithms don't work at all for 3D. Right? But with this GLR, without any change other than going from 2 coordinates to 3 coordinates, the algorithm is the same. Right? So many of these complex networks in future, they are not going to be just 3D or 2D. There are going to be surfaces that are 2D, connecting volumes that are 3D. Right? So when you use something like that, you can actually use this scheme called GLR. Right? So in this case, we have, this is 2 years ago at LCN, 3D GLR. These are like different examples. And this is 3D GSTR. This is a scheme that uses physical coordinates, works only in 3D, and we can do that. We can read that without having to do any distance measurements. All right. And also in this 3D DSTR, which is the physical coordinate based algorithm, instead of dealing with the physical coordinates, if you give this distorted topology coordinates, actually even that one performs better, right? Because the distortion actually corresponds to connectivity, and therefore the map that we have, the 3D structure that we have, is better than the 3D structure in the physical coordinates. All right, so we had multiple things going on, and one of the things that we were thinking about is the way we go about doing sensor networks. In a way, it's somewhat limited, right? So we come up with these algorithms, and we come up with these schemes, we deploy the sensor network, we implement this, and the sensor network operates. We don't do any changes. But if you look at biological systems or organisms, that's not the way they work, right? The child is born on the first day, they don't have any capability. Next day they have some capability that they learn the first day, and you build on that. And I think ultimately, when you have these complex sensor networks, they should evolve over time. In other words, they should operate first with the capabilities they have, which means they don't know nothing about the network. And over time, they should learn and become smart and so forth. Right, so this is where we came up with this idea. So the same slide I had earlier in a different way. So you go and drop these nodes, and they are clueless. They don't have anything. They don't know anything about their neighbors. Right? So in an environment, there's no addressing scheme and so forth. The only thing you can do is send these random rumors around, the rumor routing that I talked about at the beginning. Right? Now, so you start operating with that. And after some time, if you can use these rumors to develop something like a virtual coordinate structure, right? In the process, and then gradually you learn virtual coordinates, and then after some time, you can actually generate your topology coordinates and actually get a map, right? So let me illustrate this here. Somebody has dropped this, some sensors on their own, toss a coin, whatever, decide to become anchors, right? And these messages are going around. So this guy sends a message. It happens to go by this node that decides to become an anchor on its own. So it's going to include a field saying, hey, I'm at a distance 0 from myself. The message goes around, right? So this guy thinks it's at a distance 1, 2, 3. This guy thinks it's at a distance 4, even though in reality it is really at a distance 2, right? So these streamers go around, goes past another anchor, it inserts another field, and so forth. So you can see after these messages have gone around, you have rough idea of the distance, but these are not correct, right? But over time it can converge towards, it will only converge toward the correct value, because if you get a higher distance, you don't use that. If you get a lower distance saying, hey, I'm at a distance 3 from A, well, there's a shorter path than the one that I know about, so your coordinates actually converge, right? So you can actually initially, somebody drops this, you use streamer routing or whatever. In the process, you develop this coordinate system, and once the coordinate system converges, you calculate the topology coordinates, and you start collecting the coordinates of the other nodes, and you can create a map, right? So this is the network, circular network with 3 holes. After about 10,000 packets have gone in the network altogether, this particular node thinks that it is in a network like this, and it is there, right? After 30,000 messages, it thinks it is here in this particular network, and you can see the map gets completed, right? And if you look at the map at another node, that has a slightly different view because it hears different messages. It's distorted. That's fine. That's how we operate, right? We all have our own worldviews that are sometimes completely contradict to each other, right? So I think ultimately we want these networks themselves to evolve over time and become better at what we do. Right. 3D, same thing. 10,000 packets. This node thinks that this is the network that it's in, and it's there, and so forth. Right. So we call this network-aware nodes. In other words, the network after some time knows the shape of the network and where it is. Right. So compared to the biological system, we have a view of the world that we live in and where we are in that world. All right. So this is actually. So this is when I kind of started talking to various other people, mathematicians and others, to try to do different things. So let's go back to this here. So this is the coordinate system of this graph. And if you have a graph, one way to characterize the graph is by a distance matrix, right? So a distance matrix, the ijth entry is the number of hops between the ith node and the jth node. But in the virtual coordinate system, we don't have this distance matrix. What we have is the distance to these 4 nodes. That actually corresponds to these 4 columns, right? So the virtual coordinate system is basically you have an n by n network. Sorry, you have an n node network. The distance matrix is n by n, but your virtual coordinate system is really a subset of columns of this graph, of this distance matrix, right? If you select random anchors, this is a random set of columns of the distance matrix, and from this we figure out all these things. And in fact, M is about 5% of the number of nodes. Actually, very often it's less than that. All right, so this is how we start with. Now suppose, so far our coordinate system that we started, virtual coordinates correspond to a random set of columns of this distance matrix. But suppose somebody tells me, hey, you can't have all this. You're not going to have some of these elements either. Right? In other words, I don't have all the virtual coordinates. I have just some random measurements between pairs of nodes, the shortest distance. The question is, can I do anything about this? Right? So now we are kind of getting from even sensor networks to like general graph theory. And in fact, if you look at this P matrix, so I'm looking at this complete matrix, and if I look at its singular values, basically the significant number of singular values tells you the rank of that matrix. Right? In many of the practical networks, the rank of this distance matrix is very low. Right? So that means there's a lot of redundancy. So in fact, we take this thing here and we start dropping random coordinates from these columns, and we try to reconstruct this. And I will come to the method of reconstructing. So this is the original network, this is the original map that I had. Out of these coordinates, right? Remember, I have 496 by 496 distance matrix. I'm just taking 20 columns out of that. And out of those 20 columns, I'm going to start dropping 10% of the elements, 20%, 40%, 60%. So with minuscule information about these elements, I can reconstruct this with significant amount of accuracy. Why? Because this is low rank matrices. So there's this theory that has been developed over the last 10-15 years. It's also related to, some of you may know about compressive sensing, that's related to this one. Low rank matrix completion, right? So it's actually an NP-hard problem, but there's a convex version that you can solve, an approximation to that. and that is the method that we use. And this is where I work actually with this data scientist from Worcester Polytechnic Institute, and we get these maps. Right? And this is the distance error that we get. So what does this mean? This means that we don't need this entire virtual coordinate matrix. We only need a subset of these elements. So we are taking a random set of sub-columns, and out of those we are taking a random set of elements. So it's like going to this distance matrix and just taking a random set of elements and we reconstruct this, right? So what does this mean? This essentially means that we don't have to start with virtual coordinates, right? So we were actually very excited about this. So for sensor networks, it gives you a method of obtaining topology preserving maps from a fraction of the information. But in a more general sense, for general graphs, you can say you can recover the network geometry or layout and topology from a very small random subset of elements in hop-based distance matrix of large-scale networks, right? In other words, your topology map you can generate using these random measurements. You are no longer tied to the virtual coordinates either. So what we have done is we say, hey, this is not essential anymore. All you need is some random set. We started with this one, but now we don't need that. Right? Okay, this is for 3D. Works fine. Okay. So I think I'm running out of time, so I'll kind of summarize some of the other work that we have done. So this is actually a paper that I'll be presenting on Wednesday. So we started with this map. This is the distorted map that we get. Now suppose I know the actual physical location of some of these nodes, right? Somebody goes there and calibrates it. Some of these nodes know their physical location, right? So in this case, for example, these red nodes know their actual physical location, so we can actually go and stretch this map so that those nodes actually can coincide with their physical location. We get this one, right? So in other words, if you don't know any of the locations of these nodes, you can start with this map. If you start finding the actual locations of some of these nodes, you can start stretching and compressing this map to resemble the physical map, right? So we have kind of closed the loop. We didn't want this, but now you can get these topology maps that are distorted, and if you know some random set of physical locations of if you know the physical location of a random set of nodes, now you can actually come closer to this one also, right? So, all right. So this is some of the work. This is actually going on at UNSW. So we talked about finding the distance using the signal strength. What we did was essentially, if you can communicate, you have a distance 1. If you cannot communicate, you don't know the distance, right? So what we did was essentially something like this here. So now we can actually have a whole family of curves that between this and come up with different maps. So this is actually, what Anura Jayasumana at UNSW is doing. This is the control theorist that I talked to you about, right? When I met him, he basically said, hey, you have this map, but there's really a family of networks that you can create. In other words, you can create maps corresponding to the hops, you can create maps corresponding to the loss rates, and so forth, right? So again, this is a paper that actually I'll be presenting again on Thursday, using other types of things. Then he also does tracking, right? He knows how to track targets and other things. So when you have a target, you measure the physical distance and estimate the velocity and track these things. And you are tracking this in the physical coordinate space. Instead of tracking it in physical coordinate space, can you track it in this distorted coordinate space? Something is going at a constant velocity here. Here the map is compressed in some areas, expanded in some areas. What happens? It's like the velocity is changing, right? But if you are operating in that coordinate space, instead of just using constant velocity, you include an acceleration that estimates that, you can still track these things. Right? So this is again ongoing work. So there's quite a lot of work going on there. All right. So I think with that I'll conclude. Again, I want to thank the students, and it has been quite a ride since that LCN 10 paper. It's almost like I think many of the problems that you are trying to solve in large-scale sensor networks using physical coordinates, you don't need physical coordinates. As you find physical coordinates, you can migrate towards that. Again, this fits into this paradigm. You have to start operating with what you know, and over time you can absorb this information and make your solutions better and better. All right, so with that I'll conclude and open up for questions.
Okay, let's first thank. We have some time for questions.
Thanks, very nice talk. Your generalization of your technique towards the graph theory in general, but the distance metric, for example, the hop that you're using, these are bounded by the energy of transmission. So you consider the same energy of transmission. So if you vary the transmission, the hop size will vary.
Yes.
What would be the implication?
Yeah. So I had a plot. So if you let's say for example, if you increase the transmission range, your distances actually decrease because we are counting the number of hops. That's fine because that's the communication topology, right? So that's why we call this like topology maps as opposed to the physical map. So if you have large communication range, your maps shrink, taking into account the communication pattern.
No, but if sensors use different types of energy for the same graph, then you might lose the physical topology that you're currently.
Yes, okay. So two parts to that, right? My first argument is using physical coordinates is an artifact due to the fact that we are used to physical coordinates. But in networks, it's not a natural thing, right? But then you have to admit that there are certain applications where you need the actual location, right? So that is where you start with the topology map that gives you a map, and then you stretch and compress this based on the physical information available to you. Right? So you can make it approach the physical thing, but if you want it to be physical, you have to find all the physical locations.
May I go with this?
Yes.
A very connected question is, again, you didn't tell us about the density of the sensors. For example, will it also impact your observation?
Yes, actually, I briefly flashed a couple of graphs. Let me see if I can find it. So here, actually, in this graph, we have increased the communication range, right? So the map actually gets distorted. Random nodes. So even in cases like this where the communication range is larger, you get maps, but in this case the communication topology is not significantly different from the physical topology, right? So for example, if you increase the range so that everyone can hear everyone else, it will be a point. And did I ask you a follow-up question or?
No, it's okay. Thanks.
I saw that you use hop count as a metric to build topology. From what I know, it's quite inaccurate. You could have two nodes right next to each other with a hop count of 1. You could have another one that has a 50% loss rate and still have a hop count of 1. Have you considered using a metric such as ETX?
Yes. So I completely agree. Right? So first part of answer to your question is, I'm not claiming that these maps are physical maps. I'm claiming these are topology maps. You can find physical features in these maps, right? And then, as I showed in this last slide, as you get to know physical location information about some of these nodes, you can actually stretch this map and make it more an approximation to the physical map. But if you want to do routing and other things in 3D and others, having the physical locations will not help you, right? So my argument is, even in cases where you can't resemble the physical maps, it is a better coordinate system compared to the physical coordinate system, right? But once you have this, you can start going towards physical coordinates. You still have this one when you want, but when you have physical coordinate like system, you can do that also. But I am not proposing this as an approximation for physical coordinates. This is the natural network coordinate system. That's what I'm arguing.
I don't mean that you should use physical coordinates, but as a means to build a topology, you use hop count, which is just binary, it's 1
Yes,
or 0.
that's correct.
But ETX is also a virtual coordinate system. It's just like expected transmission count. So what is the PDR between two nodes?
Yes.
It's just a more precise metric of the topology.
It's precise in the sense if you want to approximate the physical distance.
Physical distance, I would expect, is like a geometrical distance.
Yes, 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 exactly.
But in this case, if we have like 20 centimeters and there is an iron bar in between, we have a low physical distance,
Yes.
but a low packet delivery ratio, plus
Yes.
a high virtual distance. This is not reflected by hop count.
This is reflected by hop counts because I have a wall here and there are two nodes next to each other, right? So the only way to communicate between these two is I have to go around this. 15 hops to come here. So this distortion actually takes that into account.
Even if it's like 20% delivery ratio, so we see the other hop, but we have a low delivery ratio.
Okay, yeah, so that comes to this other work that we are working on. So I told you, this control theorist, basically he said you can have a family of these maps. So in one of these things we are actually using the loss rate. So this is a topology map that corresponds to the loss rate. So you can have these different types of maps. In fact, you don't need all the measurements either. As I said, you can do completion of low rank matrices, and as long as you have this random subset, you can construct this networks.
Right, thank you.
Yes.
So if you're about to track a sensor, if you're tracking a sensor, this map is distorted. So what protocol do you use to reach up to the map? Because each node is on different points. In your own point of view, you don't know where the specific point of the node is.
Okay, so there are I think we are mixing up two parts. So in the network aware nodes, yes, each node has its own view of the network, right? So that is part of it. But if you go back to like the structure where you have a set of anchors and the nodes have consistent view, then all of them have the same map. Right? So we are doing the tracking on those maps. Because, for example, when a target moves, it goes past certain nodes. From that, they know the distance between them in the topology domain. They can estimate the acceleration, deceleration, velocity, and predict where the targets are. Right? So in the case where we are doing target tracking, we are using a consistent view of the map.
So is there any estimated time for nodes to get for all the nodes to get the same map each?
Yes. So if you assume that the nodes are not changing, if it's a static network, actually it can be generated and propagated quickly.
My question was actually related to this, would it consider dynamic topologies? Because if the network learning time is a lot, then it won't really consider when your nodes are moving and, to kind of adapt to that.
Actually, great question, right? So one of the criticism of virtual coordinates is like, if your network topology changes, your virtual coordinates are wrong, right? But if your connectivity changes, does the physical shape change? No, right? So for example, if you look at this map and suppose one of these anchor nodes actually disappear, powered off, so your virtual coordinates won't be valid, but these topology coordinates will still be valid for a static network, right? So in that sense, this is advantageous. So coming to the mobile networks, so if we have a subset of nodes that are static and the other nodes are mobile, we can still handle that, right? But if you have all the nodes that are basically dynamic, so that is some ongoing work, right? So suppose you have these drones that are flying. The only thing they can do is communicate, find out who they can communicate with. They can't measure distances. You can try to, as long as you can create these maps fast enough compared to your mechanical velocity movement, you can actually try to get this self-awareness. In other words, each drone would know their position in that network, right? So this is actually something that I want to do that I have not done. But you have to keep on repeating this fast enough compared to the mechanical speed of movement. In that case, it would work.
Any final questions? Okay. Not, please join me again in